Hi, welcome to video 1.4D part 2, removable discontinuities.
Have a discontinuity and we're going to remove it. So with f of x, here's the definition. If f of x is discontinuous at x equals c, but the limit is x equals c of f of x does exist, so the limit from the right and the limit from the left, don't know why that's ringing, sorry. Hi, so sorry about that. Anyway, so the limit as x approaches c of f of x exists, which means it equals the same number from the left and from the right. However, it's discontinuous at c. If that's the case, then that discontinuity can be removed by reassigning a value to f of c. Now, so that's their formal definition. The informal definition is the only kind of removable discontinuity is a point discontinuity, because that's the only one where you can stick in one number and boom, the whole thing's continuous. You can stick in one point. And as you can see here, although the function, f is discontinuous at 2, the limit is x approaches 2 from the left and the limit is x approaches 2 from the right of our function. Both equal 3, and therefore the two-sided limit exists. And therefore, if I simply redefine it as f of x equals x plus 1, where x does not equal 2, I actually have removed the discontinuity, because this one actually started out like this. And this is the thing you need to understand. The reason you get a point discontinuity at x equals 2 is because x minus 2 is a factor in both the numerator and the denominator. Now, I just want to point out that a jump discontinuity is obviously not removable, because you can't just fill in one point and the function's already all of a sudden continuous everywhere. And same thing here, there's no way you can plug in one point and have it be that way. So the only type is a point discontinuity. So to remove it, you redefine f of c so that the function is continuous for all real numbers. So as I said, to fill in that dot, you would let it equal the original function if x doesn't equal 2. And when x does equal 2, you would say, you know what, I'm going to let f of x equals 3. Okay? So again, a reminder, you get a point discontinuity when the function is a rational function. It has a polynomial numerator, polynomial denominator, and there is a common factor in the numerator and denominator. Okay, so again, point discontinuity is the only type that's removable. It occurs when you have a rational function with a common factor in the numerator and denominator. So here's just another example. As you can see, if I factor the denominator, there's a common factor, so this function will be discontinuous at, right here, x minus 3 and x minus 3. It'll be discontinuous at x equals 3. So here would be where it is continuous, which happens to be its domain. The discontinuity at x plus 3 is not removable. That's a vertical asymptote. It's the common factor, that discontinuity, which is a point discontinuity, which can be removed. So what happens is, if you have a function, which is this function, 1 over x plus 3, where x doesn't equal 3, you will be able to remove that discontinuity at x equals, 3. So if I filled in this dot, I actually would be able to remove that discontinuity. But there is no way to remove that discontinuity here. And this is just information on how to graph it, but that's not necessary right now. Okay, this is very important. This is the continuity of different function types. The main function types we'll be looking at are the polynomial function, the rational function, the radical function, and the trig function. And it will be important for us to simply know that these functions are continuous either everywhere or everywhere on their domain. Now, that means that, and because of these theorems, it's going to be very easy to pinpoint where a function is discontinuous if you're not given the graph. You're not always going to be given the graph, and of course you don't want to go through the hassle of graphing some of these complicated functions just to answer the question, what is the largest interval on which this function is continuous? So, as you know, a polynomial function has this look to it, like 7x to the 5th plus 4x to the 4th plus 18x cubed plus 6x squared minus 8x plus 7. Okay, so the n's, which are the exponents, are non-negative integers. These functions, which is like the mountains and valleys I showed you on the last 2 pages ago, this one, that's a polynomial function graph, and that's going to have a domain of all real numbers, and this function is continuous on its domain. So, rational functions, on the other hand, polynomial over a polynomial, are also going to be continuous on their domain, but that domain is going to be wherever the denominator is not 0. Radical functions, square root, cubed root, fourth root, fifth root, are going to be continuous on their domain, which is if the root index is even. Square root, fourth root, sixth root, eighth root, the radicand would have to be greater than or equal to 0, because we are not dealing with imaginary numbers like the square root of -1. But if the root index is odd, then the domain is all real numbers. Trig functions are also going to be continuous on their domain. You should know those domains. For sine and cosine, it's all real numbers. Just picture the graph, which is the wave. Tan and secant, if you think of those, are both sine over cosine, 1 over cosine. They're going to be discontinuous whenever cosine is 0 and cosine is 0 at pi over 2, 3 pi over 2, 5 pi over 2, the odd pi's over 2. So the domain is all real numbers except for the odd pi's over 2, where n is an integer. Cotan and cosecant are both over sine. They're going to be undefined at 0, 1 pi, 2 pi, 3 pi, 4 pi, etc.
And that's the end of video 1.4D, part 2.